Hello all, welcome back. So in the previous video we have stopped at this point. So we in the previous video we saw different pre-trained models, different state of the art models, which were which won the ImageNet challenge over the years. So there are different architectures, right? There are many people have tried different things, like Google had tried the Inception module thing, which gave them significant results, and some other group of people have tried these skip connections, these residual connections, which was a great improvement also. So all of these different things they have tried, and they have trained these models very carefully so that the error on the ImageNet dataset is very low. All right. So now what the idea, so the basic idea that we talked about in transfer learning was, why not use the convolution layer part in these networks and train our classifier by our own. Okay, so instead of training the feature extractor also, why not use the feature extractor from their network, and then train our own classifier. Okay, so training a classifier with a few layers is quite better than training the whole network, training both the feature extractor and the classifier both. We are reusing the feature extractor from their network, and we are training our own classifier. Okay, so that's what we are going to do in transfer learning. So yeah, first of all I want to talk about what the convolution layers actually learn. Okay, so we saw this image in one of the previous videos also. So if you see, as the initial layers, in the initial convolution layers, the features, the convolution net features in the initial layers are more generic in the earlier layers. Okay, so in the early layers the features are generic, and as you go deeper and deeper, the features become more and more dataset specific. Okay, so let me just explain what that means. All right. Okay. All right. So yeah, let me just explain to you what that means. So in the earlier layers, the features are more generic, which means they are not too much dataset dependent. Okay, so they are not too much related to the dataset, and as you go deeper and deeper, the features become more and more dataset dependent. They look more and more like the dataset. All right. So let me just explain that to you. So we have an image, there's a woman right here in the image. So in the initial layers, the what the features learn are very simple and generic features, like the pixel values, or uh, the simple features like the edges, curves, and things like that. And as you go deeper, it starts to it starts to learn more and more abstract features, like the contours, or the corners, or the different shades, or the shining properties and all. So that's all seen in the images. So as you go deeper and deeper, it will become more and more dataset specific, right? So as we went deeper into the convolution layers, we can see that it is more dataset specific, as this feature might look like a lot like this woman right here. So it is learning the features from the image itself. Okay, so it is looking a lot like the images from the object seen in the images of the dataset, right? So in the initial layers, it is not so much representative of the data set, which means there are curves and edges and all. So and these curves and edges can be seen in any data set, right? Not only this data set. If you take another data set, these curves and images can be seen, right? They can be easily recognized over there also. And as you go deeper and deeper, the features would be more dataset specific, which means the woman right here, the tire of a car, and the pole or the telephone line here, they are more dataset specific. Okay, that we are feeding into the neural network. All right. So that's what you need to keep in mind. So now we'll talk about some rules of thumb for transfer learning. All right. So how do you apply transfer learning in different scenarios? Okay. So let's say we have a data set, and we have a very small very few very small data set. Okay, we have very small data set, and the data set we have a classification task. Okay, let me just start from the beginning. We have a classification task, and for that classification task we have a data set ready. All right, and the data set is very small. I mean, I don't let's say we don't have too many data items in that data set, more like 1,000 data items or something, in thousands only. Okay, so we have the data set is very small, and is similar to the base training set. So what is the base training set? So the base training set is the original data set on which these networks have been trained. So these networks, all of these networks have been trained on the ImageNet dataset. So what I'm trying to say here is I'm trying to do a new classification problem in which the dataset is small and the dataset is very similar to the ImageNet dataset, which is a base training dataset. Okay, so at a time like that, so since my dataset is similar to the ImageNet dataset, in all of these pre-trained models, we can reuse these dataset specific features, right? So and try to like pause the video and then try to understand. All of the models that we talked, the ResNet, VGGNet, have been trained on the ImageNet dataset, right? So in those networks, in those models, the convolution layers have learned the feature extraction. So the kernels in the convolution layer are more trained, to extract the features from the images. Now since my new data set also looks similar to the also is very similar to the ImageNet data set, so I can reuse all of these features, right? I could reuse all of these convolution layers instead of building my own convolution layer and then training them from scratch again. I could reuse all of these features. I could use all of these feature extract these convolution layers, and then I could just simply change the last layer. Okay, so if you take this example, this neural network, I could reuse all of these layers, and I could just replace the last layer with a new layer. Okay, so instead of 1000 classes, if I want to do a classification task which contains only 10 classes, I could remove this layer and then I could replace this layer with a new layer with 10 nodes only, with 10 different classes only. So we are actually reusing the whole network here and then retraining the last classifier part only. Alright, so yeah, now moving on. So when the dataset is small and similar to the base training set, so when I say similar to the base training set, which is similar to the ImageNet dataset, you can think of like vehicle classification dataset. So you can like give the images of different vehicles, so and the model needs to predict whether that's a car or a bike or a truck or whatever it is. So the vehicle classification dataset, so dataset might be containing different vehicles, and the ImageNet dataset also contains vehicles, right? The ImageNet dataset also has vehicles in it, so you can see that there are many vehicles. So our dataset is very similar to the ImageNet dataset, which is a base training set. So that's why what we could do is we will remove the fully connected layer near the end of the pre-trained base coordinate. Okay, so in the when we will choose one of the pre-trained model for our task, and then we will remove the last fully connected layers and then add a new fully connected layer in its place. Okay, so that it matches the number of classes for the target dataset. Okay, so we'll remove the last fully connected layer and we'll add a new one. Okay, and then we will only train, we will freeze all the weights of the pre-trained network. Okay, so what do I mean by freezing all the weights of the pre-trained network? So what I mean is we will freeze the weights in all of these layers. Okay, we will train only these two layers and we will not train these layers. Okay, we will not update the parameters in these layers, but we will only update the parameters in the last layer which we have newly introduced. Okay, so that's what we will do. That's what freezing the parameters mean. We will not update those parameters, and hence they are called as freezed. Alright, and now train the network to update the weights of the new fully connected layer. So the newly added layer there is, we will update the weights of only that layer. Okay, so that's how you could use the pre-trained models for your new classification task if these are the conditions. If you have a small data set and is similar to the base training set, you could do this. So another example for a data set that is similar to the ImageNet dataset is dog breed dataset. Okay, so given the images of a dog, you need to predict what is the breed of that dog, whether that is a husky or a golden retriever or a I don't know, whatever, or a chihuahua maybe. So you need to predict the breed of that dog also. So that kind of dataset is also very similar to the ImageNet dataset, as the ImageNet dataset also has some animals and dogs inside it, right? It has also animals and dogs inside it, so it is very similar to the ImageNet dataset. Hence you can use the feature extractors of the convolution pre-trained models, right, from the pre-trained. So let me just explain you through an image. So let's say you are using one of the pre-trained models. So this is an architecture of one of the pre-trained models, let's say. So you're using so the green part here, all the green part here, you are reusing it. All right, all the green part here, you're reusing it, and the red part here, which is the last layer only, the red part here you are replacing with new layer. Okay, so you are taking out this layer, you are removing this layer, and you are putting a new layer in that place. Okay, and then you are training only this part. Okay, so training is happening only this part and not on these parts. Okay, so that's what we do in if the dataset is small and similar to the base training set. Now let's say the dataset is large. Okay, that you have like very huge dataset of your classification task, and that dataset is very similar to the base training set also. So at that time, what you could do is you can afford. So since in the previous case the dataset was small, you couldn't afford to train the convolution layers also, because we have a very few examples, and training the feature extractor to be more like your to be more helpful for your data for your particular task would be not sufficient. So that's why when the dataset is large, what you would do is you would use the same pre-trained model. So all the green part is the same weights from the pre-trained model, and the red part is you are actually deleting the last fully connected layer and introducing the new layers. And when you train this network, so in the previous case when the dataset was small, we were training only the newly added part. Okay, but when you have the large dataset, we can afford to train the whole network. Okay, so along with the previous layers also we can afford to train the whole network since we have a large dataset. Alright, now if now consider this case, if the dataset is small and is different from the base training set. Okay, so now we have a small dataset and it is very different, it is not at all similar to the ImageNet dataset. So some examples for that would be X-ray scans. So some medical analysis you are doing, so you are using X-ray scans to predict whether that patient has particular disease or not, or you are using satellite images. So you are using satellite images to predict whether the particular to make some weather predictions or something. So these kind of images are very different when compared to the ImageNet data, right? So this is an example of different case. So at times like this, what you would do is, so since your data set is very different, what you could reuse is, you cannot reuse the dataset specific part which is a deeper layers, you can only reuse the initial parts. Okay, so you could only reuse the parts where the convolution features are more generic in nature. Okay, so since these features are more generic in nature, like edges and corners, instead of these features where it is identifying some tire and a woman right here and a telephone line, so instead of using the deeper convolution layers, we will only reuse the earlier convolution layers. Okay, so that's what we will do. So yeah, so what we will do is we will reuse the earlier convolution layers from the pre-trained networks, and then we will replace all of these deeper convolution layers and the fully connected layers. Okay, so we'll remove the deeper convolution layers and introduce new convolution layer here. We'll introduce new convolution layer here, new pooling layer here, and we can add like introduce some convolution pooling layers like that, and after that we can introduce our new fully connected layers also right here, right? And then coming to the training part, since we have a small data set, we can only afford to train this part of the data set. Okay, so this part of the network, right? Since we have a small data set, we can only afford to train this part, and we cannot train this part because we don't have sufficient data to train all of these pre-trained models also, pre-trained layers also. Okay, and now coming to the final case, say if you have the large data set and it is very different from the base training set. So you have a very large data set and it is very different from the ImageNet data set, then you can simply like build your own convolution model, or you can use a pre-trained model like that. You can use all the layers from the pre-trained model, and you can really train the whole network. Okay, so it is the same as the previous case. You can, since the data set is large, you can afford to train the whole network, and you can reuse the convolution layers from the pre-trained models. Okay, so yeah, that's some of the tips you need to keep in mind when performing some transfer learning task. We will see some practical implementations for transfer learning in the next video using PyTorch. Okay, so yeah, thank you for watching this video, and I'll see you in the next one.